Hello everyone, my name is Jiawei Wang from Monash University. In this video, I'm going to present our work, Restoring Execution Environments of Jupyter Notebooks. As a novel programming tool, Jupyter Notebooks are now very popular because users can often put text, code, execution results together as a shared document. However, it has been pointed out that it is harder to execute notebooks because of environment issues, which also make it difficult to further reproduce the same results. To understand how serious this problem is and why it's so, we conducted a lightweight study. We cloned 100,000 Python Jupyter Notebook projects from GitHub because Python is the primary programming language among Jupyter Notebook users. We then found only 6% of them clearly provided a Python environment dependency files, such as requirement files. So that is to say, the majority of open source Jupyter Notebook projects do not provide dependency files. We then installed all of these dependencies files and found 70% of them can be installed successfully. After having installed this environment configuration files successfully, we automatically executed these notebooks in the user-provided environments. But the top two execution errors are still linked to environment issues such as model not found error and import error, as we can see from this bar chart. Both model not found error and import error occurred because Python runtime could not locate modules or APIs that these notebooks have accessed. So this is sometimes due to the version constraints are not given in the dependency files. In fact, we found quite a few such dependency files are lack of version constraints. If a user simply places dependent library names into the dependency files, then the installation manager will simply retrieve its latest version. Here's an example of execution error when the given dependent library name Astropay has been installed, but invoked API scale image has been removed in its latest version. So without knowing the actual version the original developer has used, it is difficult to set up the correct environment for others to further reuse the code. Based on these findings, we can say the users tend not to provide dependency files for their Jupyter Notebook projects, but even when they have provided these dependencies, such dependency information can be inaccurate. Therefore, we propose to address this challenge by automatically detecting dependencies for Python Jupyter Notebook. We developed the tool named SnifferDog, whose workflow is described in this diagram. The idea behind SnifferDog is quite simple. Now that Python programs in notebooks leverage third-party library APIs, so we track how these APIs have been evolving by taking historical releases of Python libraries as the input for API mapping module. After that, we firstly built an API bank that can record API profiles such as its names, parameters, and life cycles. Then for any given notebook, SnifferDog will have all third-party library APIs identified, detected, processed, and sent to API banks for API usage analysis, after which environment dependency configuration file will be outputted automatically. Although the idea is very simple, there are indeed some challenges that some of the core modules in SnifferDog have addressed. One of them is library API mapping. Library API mapping aims to process library source files to generate client APIs. Client APIs are normally like a dotted string, which does not actually refer to its implementation details. For instance, the client API pandas.read CSV are implemented in a file named underline-base.py, as we see from this directory tree diagram, but the name itself does not include such paths for others to look up the implementation file. We solved this by statically inferring runtime import relations across different Python source files. Moreover, our API name standardization will extract function calls and recover the call name to its fully qualified name. For example, the API x.y.fun are invoked by different statements, which can be seen from this simple code example. We selected the top 1,000 most important modules to query the official Python library repository PyPy, and then collected 488 popular libraries from its around 18,000 historical versions to construct the API bank. The API bank has indexed in total more than 1 million APIs. We further conducted a statistical analysis of all API data and found that more than 50% of APIs are newly added after its first release. Over one-third APIs have been removed till its latest version, and more than 5% of them have changed their parameters during library evolution. So to summarize, more than 67% of APIs may introduce compatibility issues if the dependent library version information is not known by users. After building the API bank, we evaluated the correctness of our approach. So the first task is very straightforward. We wanted to see if the APIs from the API bank is reliable. We sampled around 4,000 APIs from the API bank and tried to import all of them in Python runtime environment. The result showed that more than 93% of these APIs passed the runtime test, which indicates our both library API mapping model and API data are reliable. So after that, SnifferDog is also tested on 340 ground truth notebooks that can be executed in their original environment as well. The experimental results showed that more than 92% of these notebooks can obtain installable environments from SnifferDog, and more than 83% of them are finally executed again. So this illustrates that SnifferDog is effective producing reliable dependencies for notebooks. SnifferDog is also tested in other notebooks. We choose 728 notebooks that have failed to execute in their own environments. 223 of them are recovered from execution failures. When notebooks failed to execute in both environments, in SnifferDog's environment, notebooks failures tended to be code quality issues rather than environment issues. For instance, the bar chart compared the different execution errors in both environments. As we see in SnifferDog's environment, the number of errors such as file not found error, value error have clearly increased, whereas error linking to environment issues such as module not found error has decreased. Although our SnifferDog is effective in solving dependency issues, there are still some problems to be handled, which remains our future work. First, our library API mapping module only works for Python code at this stage. However, some APIs in Python libraries are implemented in C code for better efficiency. So we will explore to perform API mapping for non-Python implementation of APIs. And the second challenge will be our API bank only currently indexed 488 libraries, which limits its capacity for a wider range of notebooks. So we'll start to include more libraries in the near future. Moreover, we will explore approaches to detect dependencies for notebooks written in other programming languages as well, not simply Python. So to summarize in this research, we proposed a novel approach named SnifferDog to automatically detect dependencies for Python-based notebooks. We aim to address this challenge of no executability issues of Python-based notebooks, which has been pointed out by other studies. So our tool has been made open source for others to reuse. Thanks for watching.
So hello everyone. After this great talk by Jiawei, I'm happy to take some questions. So if you have any questions, please go ahead and drop these questions in the chat. Jiawei, it's a great piece of work. I will start with a question that we have in the chat from Luis Cruz.
Thank you.
So it seems that they have a paper on the prevalence of code smells in machine learning projects, and they found similar issues with dependencies in pure Python projects. Would you say that this problem is somehow relevant to most AI projects beyond Jupyter notebooks only?
Oh, thank you. This is a very good question. I would say that's definitely relevant to AI projects, but I don't have data or research or statistics to support if this is a problem projects. But technically speaking, that the Python code in notebooks are no different from normal Python projects. And you can see even in notebooks, there are quite a few AI projects. So I would say it's definitely relevant.
Okay, thank you for the answer, Jiawei. And now
And
we have
yeah, okay, may I answer another question here? I can see the chat.
yeah. Let me just drop it so everyone can
Okay.
listen. So Michael Pradell is asking, what's the main reason for the difference between installable and executable notebooks?
Well, installable issues are about dependency, probably the wrong dependency files or inaccurate dependency files, like what I wrote in the preliminary study section in my paper. But executable notebooks are basically because of code quality issues. For example, if you don't give the data to the code repository and one can download your code, but he won't be able to execute because there's no data for file IO stuffs operations. Another issue is the code quality issues such as type error, name error. These are pretty common coding issues.
So it's totally related with the next question from Michael, right? Let's say, like,
Yeah.
in particular, do you check that the notebooks produce the original results?
Well, in my paper, we used a series to publish it's a publisher work to assess the reproducibility of notebooks, and so we did check the notebooks if the notebooks produce exactly the same results. But in this paper, we believe that more notebooks we can solve their dependencies, more reproducible notebooks we will get.
So I have a follow-up on that, just to stay in the same topic. I saw that at the end of the day, you still found some notebooks that still throwing some errors related to file not found, or things related to
Yes.
not good programming practices. So this is totally related to non-reproducibility, right?
Well,
Do you plan to do something related to that in the future, or what's
well,
the
I
scope
really
of the work now?
Well, yes, we are still working on program analysis for Python code. So we hope to use the static analysis tools for discovering code defects there and how to automatically repair them. This is my current work. So these are not publishable yet. So I'm still working on that. I personally think this is
Nice. So Rahul has a question here. Is it possible to save and restore the execution environment of a partially executed notebook, like saving the session for later?
it is possible to save the environment, but that does not guarantee because Python dependencies or Python environment does not simply rely on Python library itself. It also relies on some C code libraries as well, and even platform related. For instance, some libraries, Python libraries will do some Excel operation or database operations. So this part of code functionalities are supported by some drivers. So I would say that you can save, but it does not guarantee.
Okay, I don't know, Haru, if this answered your question. I felt like something that could I run the first sessions of the notebook and then come back later, or save it somewhere else and then reopen the notebook and run from the point that I stopped.
Yes.
It's a more a technical question than that I understood that way. So let's go to the next question. This seems that Howard has some, Luis has some follow-up on his previous question. So sometimes different versions of libraries may lead to different results.
Exactly.
So this is relevant for the machine learning thing that he mentioned before? Is this technique, the technique that you presented, able to accommodate these issues?
Thank only happens to machine learning projects. It can also happens to some plotting libraries because the format and layouts are different for different libraries. But to be honest, I don't think this work can accommodate these issues because we look at source code, the API usages to infer different versions. If API interface remain the same, but the actual implementation changed, and therefore it causes different results. Our approach cannot handle. But if the API changed, we can handle that.
Okay, thank you, Jiawei. And I see another question here from Pinjia. How do you collect the library dependency info? So it's more like a clarification question.
Okay, this is our experiment setting. We directly retrieve Python library dependency files automatically, such as requirements.txt or conda files or pip files. These are very mainstream dependency for structured Python dependency files.
I don't see any other questions. If anyone has any questions, just please drop in the chat. I will follow up this question with another one, Jiawei. So you analyzed just the formal dependency information, right? Did you, for any chance, try to analyze README files to see if the information was there?
Okay, I have checked some before. So in the beginning of my work, I checked this dependency. I was looking for some natural language process techniques to extract such. But as you can see from my paper in the preliminary study part, even the structured dependency files are not always reliable, not mentioned to human text. So this text can be sometimes very vague. Like they won't use structured format to tell what dependencies you will need to install, or they will use very vague, such as you will need to install NumPy or this sort of stuff. Like so, I tried, but at that time I didn't think this is a good way.
Yeah, and I think the challenge is is something really high for if you want to go this way, if you want to go this route. So I have another question, Jiawei. Have you, by any chance, tried to use these freely available platforms to see if the notebooks are executable or installable there, like Google Colab, Kaggle, or Paperspace Gradient, whatever?
Have I ever? You mean
Have you tried
applied
to?
my tool?
Yeah, have you not there too, but try to get the notebooks and try just to run there to see if the environment that they provide already set for using this the dependencies that they needed. Because these tools they provide like a wide range of pre-installed dependencies, so maybe people will just download and upload somewhere else to try to execute them, right?
Yeah, yes. So I know what you mean. Like, in this work, we started from collecting true Python repositories, notebook repositories from GitHub. So that's actual open source repositories, and we found some of them provided dependency files, and we have got some of them installed and executed as well. But after that, we use this subset of data as the testbed, as the ground truth for the evaluation of my work. So these are actual real-world Python projects.
Okay. Okay, we just have 5 seconds. Thank you very much, Jiawei. It's a really inspiring work.